Hello and welcome to episode 8 of Astromagnet. I'm Arush Ramadurai,
And I'm Ishan Chakravarti.
and today we're talking to Sally Oey, professor of astronomy at the University of Michigan.
Welcome to the podcast, Professor Oey. When did you first get interested in astronomy? Why are you interested in astronomy?
I think I've always been interested in astronomy as long as I can remember, actually. And my mom tells me that even before I can remember for myself, I was already watching like space flights of the Gemini program on TV. But what I can remember is the Apollo program. I was a kid when the Apollo astronauts first went to the moon and so forth. And it was super exciting. And for some reason, even at that very young age, I was like 5 or 6. I was 5 when the astronauts landed on the moon. I was already super interested in space. So I think just being in that environment at that time was probably what piqued my interest.
So, can you talk a little bit about the trajectory of your career? Like, what kind of education did you get that prepared you for it?
So interestingly, I think I'll start with my grade school education because I grew up in Ithaca, New York. And one thing that I do remember in grade school was that writing was really important. And writing really helps formulate your thoughts and sharpen your thinking and so forth. And it has turned out to be one of the most important foundations of my career and probably many, many other careers. You don't necessarily think of writing when you think about science, but being able to think new ideas and articulate them and make good arguments is really one thing that writing can be about. And so that was a really important thing. I think that I learned to write well at a relatively early age. And then, of course, you have to take lots of math and science and physics in particular. I went to Bryn Mawr College, and there are a lot of physics majors at Bryn Mawr College, relatively speaking, because it's a women's college. And so there tend to be fewer women in physics, but there were quite a few at Bryn Mawr College. And so I majored in physics there. And then after that, I went to graduate school at the University of Arizona and got my PhD in astronomy.
So did you have any particularly favorite research experiences?
Well, there are so many. I think just generically, my favorite feeling when I'm doing research is when I come across something new, because that's really what it's all about. Doing science research is really about figuring out how things work in the natural world. And in astronomy in particular, you're trying to figure out what's going on out there. And there are a lot of puzzles and a lot of things we don't know. So when the penny drops and you have this realization, this aha moment that you've made a breakthrough and suddenly really understand something important and new about a phenomenon that's out there, that's pretty cool. We recently had an experience like that with my graduate student, Lena Komarova, on our most recent paper, basically, where we were trying to figure out how ionizing radiation escapes from galaxies. And we noticed that there was this big wind in this one object. And we had this really aha moment when we realized that the only way to accelerate the wind was through the action of this ionizing radiation itself. So that was like a smoking gun for realizing that that wind is basically a signature of ionizing radiation escaping from galaxies.
So, you mentioned like winds escaping from galaxies. So, is your main focus of research on galaxies?
My research program is really about massive stars and how they affect their environment. And galaxies are the host environment for massive stars. Stars form in galaxies. And one of the big questions for how massive stars affect galaxies is whether radiation escapes from them. So that is one of the aspects that we're really looking at, how ultraviolet ionizing radiation escapes from galaxies, because that radiation is also capable of ionizing and sort of evaporating, if you will, the interstellar medium and also the gas of the universe, the hydrogen gas in the universe. It's believed to be one of the ways in which that gas got ionized back in the days of cosmic dawn. So that's one reason why we're interested in that. But we're also interested in massive stars themselves. They're kind of complicated because they're so big that things don't work normally as they do in the sun. So understanding massive stars themselves and how they evolve, and then populations of massive stars. For example, the other aspect of our research program is basically to look at how stars got out into the field, these very, very massive stars, because normally they don't live long enough to get out into the field. And yet there are a lot of them that are out there, stars that are not in clusters. It turns out that they've been ejected through dynamical interactions, just through kind of binary interactions and things like that. And some of them have also been ejected out there when you have a binary system where one companion goes supernova. And then, when one star goes supernova, then the other one can be ejected from its neighborhood as well. So those are the kinds of things that we're looking at on the sort of small scale end of things.
So is what you're talking about at the end there, your research on runaway stars?
Yes. Yep. So those create runaway stars. And then, you get other interesting populations of these massive stars. So once you have two stars that are so close together that they can actually interact, you get mass transferring from one star to the other. So one star can actually grow into a much more massive star than it originally started out with. And it also acquires the angular momentum from its neighbor. So it starts spinning super, super, super fast. It spins so fast that it actually starts producing a decretion disk. You've probably heard about accretion disks where stuff is falling into a star. If a star spins fast enough, it can actually form a decretion disk, or some people call it an excretion disk. And so then when you have a little decretion disk around the star, that disk also lets you know it's there by its nebular radiation, which we can also see. So that's another consequence of having a very close binary system.
Would you be able to talk about feedback activity in nearby galaxies?
Yeah, that's the name of our research group,
Yeah.
FANG, Feedback Activity in Nearby Galaxies. So that's kind of encompasses the kinds of things that I've been talking about. By feedback, we basically just mean the effects that massive stars have on their environment. That includes radiation, as I meant, ionizing radiation, as I mentioned earlier. And it also extends to the supernova explosions, because massive stars end their lives in these giant explosions. And those obviously have a lot of kinetic energy. The kinetic energy then shock heats the gas, and you end up with extremely hot but very low density gas that's basically around 1,000,000 degrees. If you have a lot of these stars all together in a starburst, you can produce 10⁷ degree gas. And so that gas also will expand, and it pushes around the other gas. So that's also a form of feedback. I tend to refer to that as mechanical feedback. So we've got the radiation feedback, we've got the mechanical feedback, and then when the stars explode, then they also send out all of the heavy elements that they've manufactured out into the interstellar medium. So they pollute the environment, so to speak. And we can refer to that as chemical feedback, if you like. So we've studied all of those kinds of things in our research group over the years. Right now, we're focused mainly on the population of massive stars that are in the field, the runaways, as you mentioned, and the binaries, and also the escape of ionizing radiation from starbursts.
So what lessons can learning about the effects of massive stars on galaxies teach us?
I guess the greater importance of like why you're interested in this research, why you feel that it's important research.
Well, it's an area that is very cross-cutting. So I talked about individual massive stars, and then we've talked about ionizing radiation that kind of made the universe ionized at cosmic dawn. So we're talking about scales all the way from the very small individual stars all the way to the universe itself. So that's kind of fun. I think that speaks to the wide influence that massive stars have in the grand scheme of things. You can look at them just within their own galaxies or even just individual objects, which at that point, massive stars are kind of so rare that each one of them has its own personality and its own unique kind of, things that are fun to study. I've got one in particular that's just really wacko. And then then in the aggregate, when you look at populations of massive stars, then you start looking at them within populations of galaxies, and then how does that affect how the universe itself evolves?
So what
Would
is
you
the
be
real
able to
wacko
talk?
star?
Oh, sorry. Go ahead, Rush.
Sorry, what is the real wacko star that you were talking about?
Oh, there's this one that just has the most amazing light curve. So it's a very massive star. It's in the Small Magellanic Cloud, which is a small dwarf galaxy that's orbiting our Milky Way. And this star, it just has, it changes. It has this apparently cyclic brightness variation that increases and then it decreases slightly and then it drops and then it starts all over again on a time scale of maybe 14 years. But then on top of that, it's also got these monthly variations. So it increases and decreases in magnitude on timescales on the order of 30 to 40 days, which and also not quite regular. And then on top of that, it seems to also have other sort of strange variations, and it changes in color as well, according to all these. So it's probably a binary system, we think, in an extremely eccentric orbit. It also seems to have a disk that is probably a decretion disk around it. But just the behavior of that light curve is just extremely unusual. And we've had a hard time figuring out what it is, but I think now that it's a binary system with an extremely, extremely eccentric orbit, a very plunging orbit, that where the secondary actually grazes the star. And it's in a class of objects, or very similar to a class of objects that are called heartbeat stars, because the light curve, it will have a little eruption and then it will drop very precipitously and then start growing again. And then that cycle repeats itself.
What's the star called? Do you have a name for it?
Well, it has an ID in Massey's catalog of 77616.
That's the best you have so far.
It also has another ID that isn't quite as, it's also AZV 493, Azzopardi and Vigneault catalog.
So it's like a newly discovered star.
It's something that's, I guess it's been around, it's been identified a few decades ago, but it's not one of the brighter ones because it's in the Small Magellanic Cloud, so you couldn't see it with the naked eye.
I see.
Can you talk about the possible 200 solar mass limit that you might have found?
Right. So about 15 years ago or so, a little longer, we were kind of interested in looking at whether there was an upper mass limit to how massive stars can actually get, because you kind of think that's probably the case. And so we basically started just looking at all of the published existing data for the Magellanic Clouds, which, as I mentioned, are these dwarf galaxies that orbit around our Milky Way. They're close enough where we can see complete populations of these massive stars. So in terms of statistics, you've got everything basically. And you kind of take sand. Let's look at a handful of sand on the beach. And you look at the sizes of the grains of sand that you have. And you notice that there are a lot more small grains than large grains of sand, right? That's kind of usually what you find. There's usually more little things and fewer big things. And that's exactly the way stars behave. There are very few massive stars and there are zillions of low mass stars. So we just thought, okay, well, people have done an inventory of pretty much all the massive stars in a lot of these clusters of the Magellanic Clouds. And so let's just look at them in the aggregate and see if there's any evidence that there's a cutoff to the most massive, an upper limit to the mass distribution of these stars. So the more you put together in your bag, the more you can actually see what the total distribution looks like. So when we did that, we saw that there did indeed seem to be a limit of around 150 solar masses or so. So I would say that what this really means is not necessarily that there's a super hard limit. It's not as though there are no stars over 200 solar masses, period, or there are no stars over even 300 solar masses, period. But just that the distribution just falls off at that point, essentially. So that the chances of finding a star at those extremely high masses is very low, much lower than what you would have predicted just by extrapolating the distribution from the lower mass stars. Does that make sense?
Yeah, what would you say is the limiting factor there? Like what is causing
Ah,
that cutoff?
so that's a completely different and very, very interesting question that I think is not very well understood.
What's your favorite part of your job?
I would say it is waiting for those aha moments, you're working on a problem and then when you have that aha moment and you figured out something new, that's very satisfying. I would say that's the most rewarding part of the job. That's the reason why we're doing this.
What career challenges have you run into and how did you navigate them?
I would say probably one of the larger challenges is encountering one or two people over my career who have been difficult to work with. And you just have to power through and stay on top of things and keep your eyes on the prize, stay focused on the science and don't let things like that get to you.
So do you have any advice for students aspiring for a career track in astronomy?
Yeah, I guess I would say don't ignore reading and writing because astronomy may be, a science, which is very heavy on the math and science and physics, but don't ignore the reading and writing because you're definitely going to need to be able to do that. Reading scientific articles is not a piece of cake to begin with. You get used to it, but it can be hard to begin with. And then, as I mentioned earlier, writing, being able to formulate your thoughts and write down your arguments clearly is extremely important. You can have made a very important discovery, but if you can't convince other people that what you found is solid and reasonable, then that makes it very difficult. So you're going to need to be able to communicate your results. So always practice your writing skills whenever you can as well.
Is it all right if interested high school students contacted you for advice or guidance via email?
Yeah, sure.
Thank you for your time. So that was Sally Oey. To learn more about her field, check out our website for additional resources.
Thank you, and we'll be back with another episode.
Thank you so much for having me.